Welcome to This Explainer. Today, we're diving straight into mastering the visual language of dynamic software behaviors. Have you ever wondered how developers actually translate those invisible split-second operations of a complex system into something we humans can understand and, well, actually build? If so, you're in the exact right place. Let's get right into it.
Think about it for a second. Raw code? It's static. But software in action, that is totally dynamic. It's a complete flurry of activity. So I want you to think of a sequence diagram kind of like a script for a play. In this script, the various software objects are our actors, and the methods or commands they fire off to each other, that's their dialogue. And today, we're going to learn exactly how to read and write that script.
Here's our game plan for today. 1. An intro to sequence diagrams. 2. The core elements. 3. The visual syntax. 4. Modeling complex logic. And 5. We'll bring it all together with an ATM system example. All right, Section 1. Intro to sequence diagrams, capturing system interactions.
Okay, so every single sequence diagram out there is built on two fundamental cellular elements. Take a look at this really simple interaction between an order manager and an order. First up, we've got the participants. Those are represented by the boxes at the very top and the vertical dashed lines dropping down from them. We call those dashed lines lifelines. Second, we have their communications. Those are the horizontal arrows crossing back and forth between the lifelines. We call those our messages. Lifelines and messages. Really, that's the whole shebang. It all builds from there.
Moving on to Section 2, the core elements, the vocabulary of messages. So this table neatly defines the core grammar of our visual language. You've really got to pay attention to the specific arrowheads here. A solid arrowhead, that indicates a synchronous message. Basically, this means the sender calls an operation and strictly waits for the receiver to finish it before doing literally anything else. Now, an open arrowhead is an asynchronous message, or a signal. Here, the sender just fires it off and immediately keeps going. No waiting around. We've also got dashed arrows for message returns and specialized arrows for either the creation of a new target or its destruction to completely eliminate it.
Let's hit Section 3, the visual syntax, reading a diagram.
Let's take a quick guided tour through this visual syntax using an add course action. See that little pentagon shape tucked in the top left corner with the letters SD? That prefix frames the entire diagram, telling us, hey, this is a sequence diagram. Now check out those vertical rectangles sitting on the dashed lifelines. Those are called activations, and they are absolutely crucial because they visually pinpoint exactly when a particular lifeline has the focus of control during an interaction. It's like a spotlight on exactly who is talking.
The really cool thing here is seeing how dynamically the system breathes. Focus your attention on the exact moment the registration manager sends a create message over to the right. Do you notice how the course object doesn't just sit at the very top of the diagram? Instead, it's brought to life right at that precise point on the timeline. The visual layout is literally representing the dimension of time flowing downward.
Next up, Section 4, modeling complex logic, layering the details.
To really wrap our heads around this, look at these linear textual requirements for a bike hire system. The customer chooses a bike. The receptionist keys in the number. The system displays details. The customer specifies the length of the hire. The system displays the cost. And finally, the customer pays. This is a fantastic baseline interaction flow. It's super easy to read as a simple numbered list. But, it completely assumes the mythical happy path, where users never ever make mistakes. But then reality hits, and we get alternative courses. What if the customer details are already in the system and we can just skip some steps? Or what if the customer is totally unhappy with the price and wants to bail on the transaction halfway through? Honestly, it's incredibly easy to just list these alternative rules out in text, but it sets up a massive challenge. How on earth do we actually draw these invisible what-ifs into our visual system architecture? That brings us to Section 5, the ATM system example, putting it all together. Just take a moment to look at this dense block of text outlining ATM requirements. A customer inserts a card, the system validates it, requests a PIN, checks against stolen card databases. The cognitive overload here is just immense. Trying to map out complex software behaviors purely in raw text like this, it makes it nearly impossible for a dev team to confidently build a flawless system. It's just too much to hold in your head at once. So, utilizing the concept of progressive disclosure, we always start with the simplest, happiest path first.
This diagram right here shows the baseline validate PIN sequence. The customer enters the card reader passes that info to the ATM controller, which then asks the bank system to validate it. Everything returns OK, the PIN is requested, entered, processed, and validated. A perfectly straight, synchronous conversation. No hiccups at all.
But remember those messy text requirements we just looked at? Let's isolate one specific, very strict logical rule from it. The customer can enter a PIN up to 3 times. If the third attempt fails, the card is confiscated. By pulling this out, we know exactly what specific challenge we need to draw next into our diagram. Now notice how our design evolves to handle this. Over on the left, we've got our basic happy path interaction. But on the right, check out those bold colored boundary boxes. We enclose the PIN request process in a loop box, explicitly noting that it loops up to 3 times while the PIN is invalid. Right below that, we drop in an alt box, which is short for alternative. If the PIN is valid, we move on and select a transaction, else we confiscate the card. Just like that, we visually modeled a really complex text rule.
The beauty of sequence diagrams is the incredible flexibility they give developers. Here is an alternative, slightly more advanced way to model that exact same ATM logic. Notice the break fragment hiding inside the loop? Well, if the PIN is valid on attempt 1 or 2, it successfully breaks out and exits the loop early. Then, down at the bottom, instead of an alt box, we use an opt, or optional, fragment. The confiscation of the card only happens conditionally if the PIN is ultimately marked as not valid. Pretty slick, right?
And this brilliantly illustrates how these diagrams can scale up. You might be sitting there wondering, wait, if checking a single PIN takes this many arrows, won't a full ATM transaction be an absolute unreadable mess? Not at all. Point your eyes to the ref tag in that purple box. That little tag neatly references the entire validate PIN sequence diagram we just built. We can just drop that ref box right into the larger withdrawal operation diagram. It keeps everything totally uncluttered and modular, just like snapping together building blocks. As we wrap up this explainer, I want to leave you with a thought. You interact with sequence diagrams literally hundreds of times a day without even knowing it. Swiping your transit card, buying a coffee, logging into your email, every single one of those actions is governed by these exact visual rules. So, if a single diagram maps one simple ATM transaction, how many referenced fragments would it take to map the digital footprint of your entire day? Keep that in mind the next time you tap your phone. Thanks for joining me on this deep dive into software visualization.